The reason why we have GFCIs is because of electric shock, which is probably something you're aware of, but the amount of electric flow that it takes to go through your body to injure or kill someone is very, very low. Welcome. This is Stephen again with Service Plus Electrical. I'm here with David with Electrician Ed. And we're just two master electricians here to share some information with you on GFCIs. So this is a very important topic, and this is one that we've been looking forward to sharing with you. Most people have an introductory understanding of or familiarity with GFCIs, and maybe you've heard the terminology. Maybe you know they're in your kitchen and bathroom. But this is a very important topic, and we wanted to share with you guys because a lot of people don't realize the severity of it. The reason why we have GFCIs is because of electric shock, which is probably something you're aware of, but the amount of electric flow that it takes to go through your body to injure or kill someone is very, very low. And so this is why I personally don't laugh so much when I see these videos of people getting shocked. Most people just don't have the understanding. And so we have David's written an excellent article. He has a presentation. David, if you want to go ahead and get that presentation loaded up. David has put together a presentation just with some diagrams, because sometimes this stuff, we may be able to explain it verbally, but if you don't see a representation, it's a little bit harder to understand. So what we're doing here is we're doing a 3-video series. This first video, we're going to be talking about what is a ground fault, because GFCI stands for ground fault circuit interrupter. That's the name of the device, which kind of describes what the device does. It interrupts a circuit in the case of a ground fault. And so first we need to talk about what a ground fault is. And so this first video will discuss that, which is also, you could think of that as the why. So why are they important? It's because we're going to explain to you why they're important, what a ground fault is. The next video, we'll talk about what is a GFCI and how does it work. That's more of the how. How does it actually interrupt the circuit? In the last video, we'll talk about the what, which is what does a homeowner need to do and what does a homeowner need to know. So there are some things that a homeowner needs to do, and we'll discuss those things on the third video. Onto this first video, onto the topic of what is a ground fault. David has his presentation pulled up here. So the short definition here, and they say the most common definition, a ground fault is an unintentional electrical path between a power source and a grounded surface. And if I could just real quick simplify that a little more, is our electrical system, the intentional path is that it flows through the wires that we install, through the appliance that you plug in, and back through the wires to the power source. That's the intentional path. So a ground fault is anything that takes a different path to get back to the source. And so David, with that, you want to talk a little bit more about what the ground fault is?
Yeah, thank you, Stephen. This this is going to be kind of a weird looking representation of an electrical circuit. And let me just explain some things. This right down here would represent a grounded surface, but also this conductor here is attached to the ground. So technically that's a grounded surface. And as he was talking about, the intentional path would be, you've got a transformer out here on your pole somewhere next to your house. And something I want to point out real quick is that there is another grounded connection here on every electrical service at the transformer. It may be up on a pole, or you may have a transformer on a pedestal of some kind. And there will be a ground rod there, a connection to earth also. And that allows electricity to flow back up to that source in a ground fault condition, which we are trying to define here. But the normal path is that it comes from the source through the hot and goes out into some kind of a load, and then it would go back here on the neutral and back to that. The neutral is the center point of the secondary coil of your transformer. And that out there is a grounded system because it has that connection out here. That's what makes it a grounded connection. I kind of wish I would have drawn all that out here, Stephen, because that would help to explain that better. So you're going to have to use your imagination a little bit, but you'll see the ground fault. This is all just kind of to explain what a ground fault is. And also this right here is a little bit weird looking. We're not going to have a ground rod at every outlet, but this actually represents in the connection that you'd have in a main panel where your main disconnect is. So you've got your grounding electrode out here, your connection to the earth, and it's coming up on your grounding electrode conductor to your ground bar. This little wire here is very important. This is your main bonding jumper, and that's what connects back to the neutral, which would go back to the source. Mm-hmm. So in a ground fault, that would be a nice low impedance path. Anything that's bonded together, if something wrong happened in a connection somewhere, it would have a it's kind of it would still be a ground fault, even though we've sort of intended this as an emergency path. Let's still just think of it as an unintentional path. But this is our low impedance path back to ground, and that would be what we want in case of something like a short circuit, or sometimes ground faults will trip a breaker also. But we want a fast, high current ground fault or fault in order to break that fault with a breaker or a fuse. Okay. Go ahead, Stephen.
Yeah, so just to sum that up, if you can imagine, there's a pole there on the left side. You have your pole where your utility transformer is mounted on the top of that pole. That pole bonds what we call the neutral down to the earth. And that is on every pole that the power company has. When it comes to your house, every separate building, the electrician does the same thing. Of course, there's no pole, but we bond it at your house. We tie what we call the neutral, and we tie it to the earth so that there's an equal potential there. And maybe we won't get into all of that this time, but the intended path is that the electricity flows through what we would call the hot wire, through the outlet, and then through whatever load you're plugging in, whatever that may be, and then back through the neutral to the source. So some of the misconceptions that the electricity wants to get to the earth is not true, right? The electricity wants to get back to the power source.
Yeah, it only wants to get to the earth so that it can get back to the source.
Right. And so something that you mentioned in the article, which if this is something you're curious in, definitely check out the article because it goes into all this in depth. And to correct the misconception is basically electricity wants to get back to the power source, and it will take all available paths to get to the source.
That's right.
And when David's showing his diagram there, you're imagining something happens, there's an unintentional connection, and that green wire that it shows there, that would be your third prong, your grounding conductor. That makes the emergency path back to the source, that if enough electricity is flowing, your breaker or fuse will open that circuit and therefore shutting off the power to make it safe. So David, what's the difference now? Because this is where maybe people don't understand that if you happen to be, so if we've done all our bonding and stuff correctly as an electrician in the house, and we have something metal that gets touched, then that is going to get back to the breaker and it's going to or say it's going to get back to the power source and open the breaker. But
Mhm.
if we're getting shocked through our body, what's the difference there? And why doesn't that always trip the breaker or fuse?
Okay, it has to do with resistance. And it takes probably at least 50 volts for most people to break their skin. And once electricity is in you, then you're a pretty good conductor. But and it depends on how dry your skin is or how much work you've done, calluses, to create that resistance. But um, the reason why a breaker won't always trip, where you could still get shocked, is the amount of current flow is not high enough to trip a breaker or blow a fuse. And in the ground fault, that's really common. That can happen. You could have an ongoing ground fault that's going on. We're going to get into what it means, but essentially what's happened, and you're going to see in just in a minute or two, that the current is traveling through the earth or through grounded surfaces that are connected together to get back to the source.
Mhm.
But the impedance, this may be so great. And what I mean by impedance is that's the total resistance, of every part of the circuit that it's flowing through. It may be high enough to where it bottlenecks or whatever slows it down, and you never get up to that 15 amps to trip that breaker or 20 amps. But it only takes milliamps to throw your heart into fibrillation
Mhm.
and to potentially kill somebody.
So when we're
Milliamps,
saying
that's
milliamps, we're talking like 15
thousands.
amps is a breaker,
Yeah,
is a 15 amp breaker, which
yeah.
doesn't even trip at 15 amps unless it's going for such a long time. We won't
Mm.
get into that, but we're talking a thousandth of that amount of electricity flowing through your body to
Could,
get your
yeah.
heart out of whack. And
Hmm.
so that's the importance here, and that's why the GFCIs came into play. Um, you want to keep going on your presentation there, or is that a good stopping point for the next video?
Um, well, I don't think we've really described the ground fault very well. So,
Okay.
right, this just representing potential, and I'm showing that I've got an open circuit. From this point to this point, I've got 120 volts because that's what the neutral and the hot are up in the transformer outside. Now, if you've got a person and somewhere along the way, they they make contact with the system with a hot point along the way. Now I'm showing that you've actually got current flowing. Before it was just potential. It was just voltage. But now it's broken the skin. It's going down through his arm, through his heart, through both legs. And I'm showing it this way because he's got 2 points of contact. If you were standing on one leg, you would have more resistance and you would get less current flow. But here you've got twice the amount of contact.
Mhm.
And here I'm showing it's not just flying up through the air here. It's actually climbing the pole and going back to that neutral point in the transformer. And here's
Mhm.
another good path right here. It's going up through that ground rod it's found and through the grounding electrode conductor and the main bonding jumper through the neutral back to the source. And if it was high enough, it would trip a breaker, but we don't want to depend on that because that's way too high to be flowing through a person's body, and that could definitely kill them. So we've got to stop that somehow. You could stop it any way, at any point. Um, Electricity has to flow in a circuit back to its source. Um, and anywhere along that closed loop, if you open it, you stop it again and it goes back. But this could be something that you can't let go of. So we don't want to depend on that either.
Right, because if you're getting shocked with too much current at a certain point, depending on your body mass and all that stuff, it gets to a point where you can't actually control your muscles anymore, right? So you're
Yeah.
holding on too tight.
Yeah, Charles Dalziel, I don't remember when he came up with this. When did you say it was invented? In 1971, I think.
1971 is when it started being phased into the code.
Okay, so it was probably in the late 60s where he was doing his research. And he came, he tested a lot of people to see how they could handle it and the effects of electricity on a person's body. And I'm sure that most of these volunteers didn't realize what they were getting into when they signed up, but that's some interesting studies that you can look up as well. But I think this is probably a good point to stop here, and then we'll get into how the GFCI works in the next video.
And so now, so we've talked about what the ground fault is. It's the unintentional path. And now we know that if that unintentional path is going through your body, it's extremely dangerous scenario. And that's where we're going to end this video. On the next video, we're going to be talking about what is a GFCI and how does it work. And so thanks for joining us here. If there's anything here that needs a little more explanation, message us on Facebook and or comment on the YouTube video, and we'll be happy to expound on that. Thanks all. See you on the next one.
Thanks.